I'll be quickly introducing, the challenges and solutions that we see coming in PIC testing, photonic integrated circuit testing. So Kevin, please, let's move on. Yeah, the main points of my talk are exactly these. First of all, discuss a little bit of the testing needs and challenges nowadays that we see from our many different customers and projects, and what are the solutions that wafer level testing enables, and a few takeaways. So let's go to the next slide. Next one. The next one. Yeah. So very briefly, just an introduction for those of you who don't know VLC Photonics. So we are a design and test house based in Valencia, in Spain. Last year, actually, we were acquired by Hitachi High-Tech, so we are now part of the Hitachi group. And what we provide is all kinds of services for developing photonic integrated circuits. So starting from the very basic consultancy to define optical architecture, then the core activity of VLC Photonics, which is the design and layout of the different components and circuits of the photonic circuit. Then we are a fabless company, so we outsource the manufacturing to more than 20 different foundries in all the main material platforms. We work with silicon photonics, indium phosphide, silicon nitride, PLC, and other exotic platforms. And then what is, I think, of most importance today, we have been also for 10 years working on the chip and now wafer level testing and characterization of photonic circuits, while leaving the assembly and test for different packaging partners we have also worked with over the years. So let's focus first then on the chip testing and wafer level testing. Kevin, please. There is something that is very clearly acknowledged nowadays, is that photonic circuits, even if they have matured very much over the years, these last years, they are still not as mature as electronic circuits. We are like 30, 40 years running behind. And this means that foundry PDKs are not as developed. We don't have, in many cases, enough information on the PDKs or tolerances or things like that. Component libraries are not that extent. And in general, the yields of the fabs is not that high if you compare it. So because of all this, it is still very critical to do very extensive component and circuit level characterization when we develop a product. And this means that we have many things that involve this characterization and testing. First of all, the optical probing, optical alignment, which is much more difficult than in electronics, is 10 to 100 times more difficult due to the very strict tolerances. Of course, we have to do not only electrical measurements, but also optical and optoelectronic measurements. And then all the processing of this data and eventually finding what goes wrong, the root cause analysis, is also quite complex. And of course, that is on the engineering side, let's say prototyping, characterization for that. But when you move into production, into higher volumes, scalability becomes an issue. You still require functional circuit testing, even if foundries do the metrology on the PCM cells. It needs to be done very fast and very low cost if you want to achieve high volumes, and you need to be able to short wafers or non-good dies. And yeah, in general, parallelization is hard. So if you go to the next slide, why it's hard in general testing? Well, first of all, you require a certain infrastructure, which means investment in clean rooms, probing stations, instrumentation, which can be very, very expensive, stocking of consumables, and eventually also redundancy of all these things, because if you are embedded into a testing campaign, into a very tight timeline for product development, you cannot afford an instrument or a probing station that is down for some time. Of course, then you also need the engineering expertise. So you need people that are expert in automation, in photonics, engineers on data processing and analysis, and of course, be able to have everything calibrated and with certain quality process in place. And finally, of course, timing, which is of an essence in terms of procurement of all these infrastructure, equipment, components, etc., hiring of your engineering team, and of course, once you have everything, being able to install and configure that for production in a short time. So that puts a lot of pressure on the timing. So if you go to the next slide, Kevin, please. That's where wafer level testing comes into play. I think it's solving many of these issues. If you go to the next slide, what is used for automated wafer level testing is it's now enabling the automated identification of non-tested dies and non-good dies, and this enables you to short good dies and wafers. And of course, as designers, as we are, it helps you to feedback all the design models with all the test information. So you are able to iterate on the building block design, on the circuit design, with a lot of data that enables statistical parameterization. And of course, this also helps to, as Andrea said in the past, to provide feedback to the foundries to increase the fab yield. And this eventually helps to accelerate the development and the volume ramp up. So if you go to the next slide, I'll show you what we have been working with Ficontech on the last years. This is a machine that is now in our clean room, provided by Ficontech. It's a full production enclosure wafer level tester. I will not spend much time on this because it has been presented in other events, but it's basically a tool that has image recognition capabilities with different probes for fiber alignment and electrical probing as well. Fiber including only individual fibers, but fiber arrays.
There was a lot of technology and also know-how built up over the last year, and I can offer this, and Inigo specifically wants to do that, to offer this knowledge to other companies, because it doesn't make sense that everybody reinvents the wheel here. So there are prober companies in the market, which are mainly coming from the electronic test side. They're very, very capable, but testing optical devices requires some different know-how than what is usually known in the electronic probing. And this knowledge, and this is why we have this set up this web meeting like this. You need instrumentation. You need to know how to test the wafer, and you need the machine itself. And that there was a lot of things built up over the last year, which we would like to offer to other people. And specifically, DLC can help to speed up the either service test as a service, or helping other customers to speed up working with our machine. So it's an offer to the market, and I think it's very valuable.
Can I ask Inigo, did you know what you were looking for when you went to the market looking for a system?
Well, yes and no. We had some clear ideas of what we needed, because as a design house, we need to be very flexible. We work with many different technologies, different platforms. So on the one side, what we needed is a lot of flexibility on the tool. But on the other side, it's critical that a wafer level tester is stable and it's fast enough, and it has also a very user-friendly graphical user interface and programming way, because this is essential for operators, which don't need to be like PhD level, right? So it was a process of discovery together with Ficontech on the final configuration of this tool and its accessories. Yes.
And previously, this has all been done manually.
Yeah, up to now we had some semi-automated testing setups, which allowed for basic die-level characterization and even electrical wafer-level testing, but not fully automated optoelectronic wafer-level testing.
Okay, good.
And specifically, the keyword there is multi-project wafers, because the functions are all different, the pattern might be different, and that's what we accomplished to automate fairly well, I guess.
Yeah, absolutely. Keep in mind that we work with small wafers and big wafers, from 2-3 inch wafers of, for example, indium phosphide, up to 8 or 12 inches of silicon photonics. So we need a chuck that is flexible enough on that. And then the configuration of the probe arms needs to be flexible, north, west, east, south, to accommodate all the different testing schemes. So you will see that in the next slide. So there you see that the chuck is very flexible. It's also thermally controlled. We have full flexibility on the probing side. So the Ficontech tool is enabling that. And also the cameras are allowing for all kind of image recognition on the patterns, on the fiducials of the chips and the wafers. Yeah, so if you go to the next slide, we have been testing that on vertical grating couplers, which is the most usual configuration for wafer level testing. And we have achieved very good repeatability here in the order of 0.1 dB in silicon photonics, 0.4 dB in other technologies, and less than 4 seconds optical fiber alignment. But one thing that is, I believe, two things that are worth mentioning here is that First of all, the tool is also capable of doing edge level, wafer level testing. So if you are able to dig a trench in the wafer and embed some, we'll discuss this later, we are able to do edge coupling. But also, as you can see in the lower left corner, we are able to do die level testing as well. As long as dies are properly placed in a platform, the tool is also able to work at die level, which is proving very handy in some cases when you have pieces of wafers or individual dies, but you have many of them. And also, as Torsten said, it's not that we only offer the services of testing, photonic integrated circuits, chips, or wafers to customers, but we also, first of all, partner with PhiContech to extend that same setup or configuration of the whole wafer level testing tool for customers. So we can support on the photonic engineering side to be able to scale that up at the customer facilities or through an OSAT. And then also to be able to help other customers to develop their own processes on the PhiContech tools. So we are very, very tightly collaborating on that.
Torsten, we have a question in the chat that is best to bring it in at this point, I think, in the presentation. We have a question from Maureen. Can the equipment be used for MEMS and MOEMS testing? That's the first question, and I think the second question is maybe a bit more difficult. Can it be operated under vacuum during testing?
Yeah, okay. So first question, yes. Actually, the tool is agnostic of what you actually test. So we have been doing some projects where we are able to test anything that can be vertically probed, like, for example, photodetectors or VCSELs. And MEMS testing, as long as you are able to do, I don't know, electrical probing of the MEMS, why not? Of course, you will be able to do so. Vacuum, no, it's not something that we are implementing now. So the chips are tested in a room temperature and in an open atmosphere, so it's not under vacuum. No.
Okay.
Not sure if it could be implemented. Maybe this is a question for Torsten.
I got the question. So for we're working on solutions for very high and low temperatures, but vacuum we have not considered yet. It would be also difficult to get the motion control into the system because actually the active alignment units that come from top. So.
Yeah.
And we have another question. Let's continue with that because I think it's the right time to bring it in from Jasper Jans. Would this setup also support fiber array alignment? I think, Jasper, then you definitely need to tune into the webinar next week. But Inigo or Torsten, perhaps better if you have a quick response to that question. Would it also support fiber array alignment?
Yeah, it's the tool is aligning individual fibers or fiber arrays. Yeah, both are supported.
And both vertically and horizontal capabilities. So this Periscope approach in the trenches also work with fiber arrays.
And I think, Jasper, if you have a look at our website, there is a promo video on the VLT system where we actually specifically state that it can do fiber array alignment above input-output ports above a wafer. Hope that answers your question. Okay, if there are no other questions or comments, then move on. Okay, so the next slide explains a little bit more of this edge coupling capability. So the tool has been successfully demonstrated to do edge coupling in trenches of wafers, right? So if you are able to dig a trench enough to embed some kind of 3D printed periscope into this trench, you are able to actually perform edge coupling or bad coupling into waveguides, as you can see on the diagram on the right. And by doing this, enabling edge level wafer level testing. So in some technologies, this is important. For example, in silicon nitride, where most of the coupling is done on the edge side, or even in silicon photonics, where using of vertical grating couplers may be very convenient, but on the other side, they are limited in bandwidth. So if you want to exploit all the full bandwidth and also maybe achieve lower losses to standard single mode fiber, edge coupling is really needed. So in the next slide, you see, for example, some wafers with these trenches here. There are different trench configuration. You can see one of them here. And then the very small 3D printed periscope, which has the advantage also that can be defined or custom designed to adapt to different mold field diameters depending on the waveguides that you are coupling to and the
material platform. So that's very convenient. Go to the next slide. I wanted to emphasize just to end up my presentation, how key are speed and repeatability when you are doing wafer level testing. So just to show you some examples, right, of different projects. In the case of first project, it was six-inch wafers with more than 300 dies. In every die, there were many structures. So in total, it was more than 5,000 structures. And for every structure, sometimes you need to do more than one measurement. So in total, it was in the order of 50,000 measurements if you would be to measure the whole set of structures and wafers. On the other one, it was a silicon photonics project, 2 8-inch wafers, more than 1,800 dies, more than almost 15,000 structures, and in the order of 50-60K measurements. And in the last project, for example, it was only individual dies, not wafers, but there were many of them, and with many structures and many measurements in all these structures. So what I'm telling to tell here is that being able to probe both electrically and optically in a very fast way and accelerate the trace acquisition time is really essential if you really want to scale up. And of course, as you can see, the amount of measurements can scale up very quickly. So if you are scaling up also in the number of dies or wafers, it's essential to build a smart characterization plan, because otherwise it can become impractical. Another very important point is repeatability. Coming from photonic integration, most of the times people are used to die level testing, and this is done most of the times manually. And the alignment here is quite poor. So the repeatability is in the order of 0.5 to 1 dB. If you are using automated wafer level testing, you ensure that all the alignment and trace acquisition are done fully automatically. There is no variation by temperature, by mechanical stability, and things like that. So you can see here a map of repeatability over 10 measurements of the insertion loss in a wafer. And you see that in average, we are in around 0.1 dB repeatability, which is, I would say, pretty good. There is still margin for improvement here. In the next slide, you see a little bit more information on here, because it's important to differentiate between characterization and testing. Characterization is done when you are doing prototyping and engineering, and your objective is to be able to test every device up to the limits. While when you are doing testing, it's all about sorting what are the good dies versus the bad dies according to some pre-established criteria. Okay, so when you are doing engineering, you find all kinds of funny stuff when receiving wafers, especially when foundries are doing process development or you are testing new building blocks that reach the limit. And here you can see, for example, in the top, a pretty decent wafer where there is not much variability between the different reticles. And you see that the deviation in the different measurements, for example, in this case, we are talking about insertion losses, is pretty similar for all the reticles, also in wavelength. But you see also different variations when things go wrong, right? And this is the kind of things that you are only able to detect when you do wafer level testing, because if you only get one reticle, you are not really seeing the whole picture. And for example, in the lower left corner, you see a very difficult case when some of the reticles are performing bad, some others are good, and it's very hard to do the root cause analysis here on what's going wrong. While on the right side, you have a wafer map that is clearly showing that half of the wafer is not being processed properly, right? So once you have all the wafer level testing information, doing the root cause analysis and understanding what went wrong in order to improve the fab process and the designs is also one of the most important things. And this is all about photonic integration expertise.
Inigo, so I guess the important takeaway from these last two slides is one, that the automated wafer level test is enabling, let's call it big data, big statistical data on the quality of the devices across the entire wafer, which was previously, from a resource point of view, just not feasible.
Exactly. And it gives a whole new insight of the performance of the chips, the circuits, and the yield of the fab process, which is very important for foundries, for example, when they are developing their PDKs, but it's also very important for customers when they are building their own component libraries and circuits for production.
Yeah. Okay, thank you. Please continue.
So that's mainly the whole thing I wanted to introduce. I will just leave you with some takeaways in the next slide. Yeah, the next one, please. which is that indeed wafer-level testing is really a must when you move into product development, and it's also important to do characterization when you are doing prototyping and engineering, and really high volume testing when you are moving into pilot production and volume ramp up. So we have been working with many customers over the years on this. We have a lot of experience in different material platforms and a fully ready lab and engineering team. And one of the important things I wanted to emphasize is that beyond also the redundancy that we have built in over the years, all our processes are ISO 9001 quality certified, and yeah, we have all our setups calibrated. So I think this is also important when you really get into serious product development. So that's all. If you have any questions, I'll be happy to discuss openly.
I have a few. I don't want to. Okay, so good, very done, well done, Victor. We have a question from Victor Sishkin, the guy who won the giveaway today. What was, and actually this couples in well to a question I have. What was the trigger for Hitachi to acquire VLC? And if I can add to that question, what has changed then for VLC through the interaction with Hitachi?
Mm-hmm. That's a very good question. So Hitachi or Hitachi High-Tech, I would say better, they have been a leader in supporting telecom and datacom companies developing components and modules and systems over the years by providing all the support on the microassembly of components and procurement and acquisition of different parts, and in general the logistics to scale that production up. However, photonic integration has been a key enabling technology for telecom and datacom products in the last years, and Hitachi High-Tech was missing this kind of engineering side of things. That's why that was the main reason why VLC Photonics was acquired, and it was actually pretty complementary because we come to extend the service offering for all this development based on optics and photonics. That was mainly the trigger, also based on our experience over the years, our well-known brand and expertise on all the different material platforms and application markets. What has changed? Well, we have been growing over the last 10 years, but of course now being part of Hitachi is a large corporation. Many things have changed. As you can imagine, there is a lot more bureaucracy, which is not nice. But of course, that's something that you have to live in when you are incorporated into large companies. And this also gives you Hitachi High-Tech has been giving us a lot of visibility all over the world, has been growing our sales network, of course, supporting our customers to grow in terms of facing larger developments and scaling up into production, especially with all the partners that they have in Asia as well. So it's giving us mainly the robustness in terms of financials and legal and logistics to really face large product developments and projects.
Victor has another question. Sorry, I had to retune. Victor had another question, and that was coming back. I think it was mentioned on one of your slides, Inigo. Victor is asking, how long is the fiber array active alignment? And I think it's a few seconds. Is that right?
Less than 4 seconds, but it depends very much also on the coupling structure that we are using, the type of vertical grating coupler or the type of edge coupler, and how it's designed and what material platform, what type of fiber. Also, we work with specialty fibers. So it's hard to give a number here, but from what we have seen, standard vertical grating couplers, single mode fiber, below 4 seconds for sure.
Okay, and do we see any different times for the 3D printed periscopes? Or is it similar?
No, not really. Very similar.
But there's mainly the preparation of that. So the vision alignment before you move into the trench. The alignment itself is easy. It doesn't change the time.
Okay, but the trenches need to accommodate the periscopes, of course, and we're back to the topic of design for testing in that case, aren't we?
Yeah, what is important is also that people wanting to use this kind of edge coupling approach takes into consideration when they are doing the design to include these trenches. And if somebody is interested, we can give more details on the design needs for these trenches.
And Victor's on a roll today. We have another question. What about Lidars and sensors? Is Hitachi developing this with VLC too?
Yeah. So keep in mind that Hitachi is offering services to develop all kinds of products based on optics and photonics. And they are mainly focused on optical communications because traditionally that has been the biggest market in telecom and datacom. But of course, you know, there are many other markets opening up, like Lidar, like sensing, like quantum, where of course VLC and Hitachi will be offering services here. Yes.
Okay. I have one topic, and actually, Andrea, this is something you mentioned in our rehearsal. Yes, everybody, we rehearse yesterday, and that is maybe that we should start a conversation about RF. We've been talking about optoelectronic testing of PICs, and that is what the system can do. But of course, it's actually three regimes of signal that need to be tested, that need to be acquired. There's the DC or the quasi DC electrical signals. There's the opto aspect, optical channel aspect. But there's also the RF component, which we haven't touched on at all today. My question, I guess, to the panel is, do you see that as being important? Do we know what the status is or what the requirement is for RF within a system like this at this point in time?
So if I start, so we get the request for RF testing all the time. I personally don't know if it's only for the characterization or if it's also for the large volume testing. So at the moment, most of the systems we are deploying, it's for characterization, and for sure, the more flexibility you have, the better. I'm not sure, Inigo, maybe you can tell it from your side.
Yeah, I fully agree, Torsten. For characterization, there is really a need, and we are also being requested that, and we are actually offering services on that respect. We are able to reach up to 50 gigahertz RF testing here at VLC Photonics, and actually we would have access to be able to reach up to 110. But the floor is open for debate if RF is needed when you move into high volume testing, or if some more basic measurements, maybe only at the DC side and optical side, are enabled to qualify the chips or the wafers, and then move them to assembly where more thorough RF testing is done, especially because Andrea said, the packaging in itself may modify the RF response.
You agree, Andrea, by the looks of things?
Yes, I absolutely agree. It is obvious that the final user and the designer think about the performance at the RF level. If you design a modulator, you want to see the modulator working correctly at the frequency you plan. But the wire bonding, the connector, the cable, or the electrode that bring the signal to the device, the driver itself, and the combination driver and load cannot be thought separately. So you have to see them together. But I go back to what I said during my presentation. Now, find something equivalent. So maybe measure something else at lower frequency that permit to extract the information for the working at high frequencies.
Okay.
So this can be the way to avoid direct RF testing on wafer.
Good, thank you. I personally have no other questions. One thing I do need to take into account, Torsten, I believe you need to go.
I actually need to go as well.
Okay, then we have a couple of slides to round off, but I guess what we'll do is we'll just kill it here. And if people want to view the rest of the slides there, just about how you can get in touch with Ficantech and where you can find other materials on the website, then watch the webinar per view on demand. It will go up online over the next couple of days. It will be non-gated, so that we can share this material with Andrea and with Inigo, and they can post it themselves. Thank you, everybody, for taking part today.
Thanks so much.
Torsten, Andrea, Inigo, thank you very much for the discussion, and to the viewers for your contributions and to the questions. That was a very interesting topic today, and I hope that was useful for everybody who was involved. Thank you indeed.
Yeah, thanks a lot. I just dropped my
much.
email on the chat in case somebody has more questions. Thanks a lot.
Yes.
It was great.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
No problem.
Bye-bye.
If you want to find out more about PhytonTech, you can go to our webinar page, follow the QR code. We have recently, you're registered anyway, so you have access anyway, but maybe you can pass on the information to others. All of the previous webinars on our website are now freely available. You can, of course, also go to our homepage, and of course, at any time, feel free to get directly in contact with PhytonTech, either locally within Germany, within Europe, or at any of our other locations. Kevin, next slide, please. Around the globe, in the US, in Estonia, in Ireland, in Shanghai, Shenzhen, and Thailand. We will have some news in the short term regarding our activities in the USA, and there will be more demonstration of what that means when we attend the Photonics West event in 2022 at the end of January. Again, okay, last slide. Thank you everyone, to everyone involved. Kevin, thank you for taking care of the technical side. I hope that was useful to everybody. Again, to our viewers, thank you everybody for watching, and to our guest speakers, thank you indeed. Goodbye.